Okay.
And we're live with the next talk at Meetings. It was 2025. Now, Gabriel Valenzuela will speak about PetriNet Studio, architecting a SaaS simulator in modern C++. Gabriel, I'm looking forward to your talk. Please take it away.
Thank you, Jens. Good day for everyone. As Jens says, my name is Gabriel Valenzuela. I will talking about this project. It's a project I'm working currently of my master degree thesis. So I hope this presentation will be interesting for you. So I will start with a simple question for you, and probably most of you will agree that sometime in the working day, we have to debug a race condition. And that race condition should not happen, never happen, but it's hard to make a debugging of a concurrent system. So what if we have a way to diagram a concurrency and make this representation of this model works in single time? So that diagram, I will try to comment this in this talk, is a Petri network. This tool allows us to make a concurrency diagram and make a translation directly to our code without any other modifications. And that is the reason we are working on this simulator in the CAA platform. We turned it into distributed simulator using the feature of the new standards, the C++ 2023. And we want to highlight this story and performance architecture with formal methods. This formal method of PetriNet, we can translate this model to real system, and this is where math meets with this ++. Through an important topic I will explain later, which is the state equation. So, about me, I am computer engineer in Universidad Nacional de Córdoba. I am from Argentina, Córdoba. I'm pursuing my master degree in the Universidad Nacional de La Plata. Also, I have the fortune to be professor at the same university where I study, member of the IEEE, Computer Society, and young professional member. I'm working as developer of C++ in WhatsApp, and also I am research in the concurrency microservices. One important topics about I will repeat constantly in this talk, complex system, and PetriNet, of course, which is the here of this talk, right? So, what is the agenda today? Make a context and motivation, explain why this is important, define the objectives of this project, explain what is the standard equation, define the architecture of the project, what design patterns we are considering, and what features of the more C++ we will implement, the design of the algorithms we are working in this project, some performance and risks, because every project has a risk associated, so we consider these risks, and some questions to further analyze, and finally closing. Yes? So, to make a recap about the PetriNet, which I have the possibility to present you in the 2022 meeting, C++, is a tool for modeling system not very new. It has at least 16 years old. So it was introduced by Carl and Petri in the PhD thesis at the University of Bonn. We can see Mr. Petri here. One of the first mathematical model for concurrent computation, that is when PetriNet will become popular. But it's not only for concurrent computation, we can apply it for modeling a large variety of systems. It's like the possibility of using this model in a variety of systems, not only for concurrent computation or computer science area. This PetriNet is a representation system like a bipartite graph where we have plates which holds tokens and represent the state of the system, transitions that consume or produce tokens and represent events associated to the system, and the tokens, of course, is the resource connected by arcs which define the causal relationship. So a marking, that means the states of the tokens in each one of the places of my PetriNet is the system global state. So we can start a modeling system for initial mark, which represents the state initial of my system. And every time my system interacts with a terminate environment, or because I am making a simulation, this marking will be involved, and this mark involving will represent the system state. So, in a quick way, it's a mathematical model, I can say, for concurrent system, but applied to not only concurrent systems, to many systems more. The formal verification and visual representation, and we can extend these Petri nets for traditional place transition network when we have only place and transition to extend with another types of arcs, with inhibitor arcs, reader arcs, reset arcs, wards, and also with time. Time is a possibility to apply in Petri networks, which is useful for us because every system has a time associated. So, why does it still matter? Why some areas keep research about this topic? Because it's important for formal verification and visual reasoning. Yeah, we have a way to make a formal verification of system, of our design, and visualize it. It's natural fit for concurrent and distributed system because we have the possibility to model this system with PetriNets. It's applied in workflows, embedding control, protocols, performance, model system for IoT, intelligent artificial. We have, for example, for aircraft, in many application control system, for example, we can also model this with PetriNets. And keep a highlight about this. PetriNets are a visual debugger, a design tool for complex systems. All the systems, a control system, all we develop every day on works, on a daily development tasks are complex systems. Are not complicated, are complex, and have many interaction between the system, and a way to design and visualize this system is through the PetriNets. So what this project? Why we making this research and implementation project? Because the existing PetriNet tool for academic purpose is few. Many of them are all not keep it anymore. Keeps a monolithic approach. We need to install this application in a single machine, and we are the only one to execute this tool. This is text only. We don't have in our research any reference about cloud-native simulator with distributed compute backends. So we need this empties and say, okay, we need an open CSA platform, not only for teaching, it's also for analyzing and research and for industry too. So we want to move from the problem of the legacy. I apologize for the mistake in the image, is GA, of course. I am not very good designer. For the legacy problem of having these old tools in language that don't scale, or algorithms that implemented a old way to analyze PetriNets, to a cloud-based platform that allows to use microservices to interconnect every single modules in efficient ways using the approach of the C++, because C++ allows to interact very close with the hardware and take advantage of the microprocessor capabilities, right? So the problem was we have the model of Petri Net, right? We move this thoroughly through our interpretation and our form to generate codes by hand. So we lose guarantees. It's complex to do, and we have error prone because we are humans. It's of course we have error prone. So the inspiration is based on this paper by Mentre, Bicolini, and Daniele, included in the sites of this presentation, where we can execute the model directly to standard state equation, for example, in the FPGA. So the model is the representation of the real system. We don't need anymore translate this model to represent the logic we made in the drawing in the code. So the goal of this project is bring this philosophy to the cloud-native C++ backend. And we can see that PetriNet has a semantics that fits to every domain. This is an image from Michael Diaz's book, where not only place transition nets span of semantics through colors, and colors, it means we have to add in a property to a token, yes. Also, we have the possibility to extend to time and stochastic PetriNet. For example, studying the fire sequence, I will explain what is fire later, of the network, the involved of this marking, I'd say early to a Markov chain, for example. So the core, the essential feature of this project is based in this equation, which is a mathematical equation. It's only sum two vectors. We have the next state of marking as the current state plus the incidence matrix, which represents the place transition arrangement of the network, which is always the same. The fire sequence is sigma, and the standard vector, and the matricial product with A, which is the matrix of reset tokens, where the standard vector is an AND operation, one cycle, is the AND operation of several vectors, the enable, the inhibitor, the reader, the words, and the time windows vector. This is the core of C++ engine. So in a very top level, we are making this implementation in our code, also taking advantage of several features to C++, like span, MD span, and so on. Yes, I will try to guide you our proposal design, but keep in mind that this is the core. This is the beauty of our project. A simple sum. So, as we are making a microservices architecture, we have several services serving to the user through a front end using React, a Golang, because Golang is also a compiled language, and I like it, which is the orchestration through handle this interaction between the canvas and the backend, right? We can say it's the man in the middle between C++ and the front-end user. And using asynchronous communication with RabbitMQ, we can consider to use Apache Kafka through gRPC to improve the communication between remote code procedures, or we can use traditional API REST. We have our C++ engine, which is the standard equation execution plus some analyzer for algorithms that we explained later, and the storage to keep the PetriNet markup language / JSON format, trying to keep schemas for single copy. We're using flat buffers for this project because it's more easy to read this information that will be very large, right? So we are making a software flexibility plus optimal hardware and GPU acceleration, because this operation of making a zoom, we are not only can do it in the microprocessor, we can take advantage of the parallel programming of the GPU. So at the very top level, we have this C4 diagram when user connect to our PetriNet Studio and PetriNet Studio connect with any one of the service we are considering in the backend, which is the auto provider, the RabbitMQ, the MongoDB for storage, the Petri network in the JSON format, and execution service and telemetry like Grafana and Prometheus to handle the consume and using of this. Related with the C++ module, we have the each one of the module with a single responsibility and analogous for each one of the paper association. The model for matrix program, the match, which is the instance and kernels, the calculate state equation, the engine to run this algorithm, core algorithm. Right time for pool, we have also the monitor design patterns, I will explain later, timers and telemetry, the I/O to handle the input-output operation. We are using Glaze because we use the potential of the reflected in the C++. And of course, the possibility of using board implementation through single instruction, multiple data, or GPU facades. So, some patterns are we considered on design as the design behavior of strategy for firing policy, because every time we make a change of the network, we are firing a transition. This transition produces this change in the marking of the network, and this one of the transitions has a priority to be fired because we can have two possibilities to fire a transition, and it's important to highlight that possible is our design our model of system has two transition enabled. One could be the system dead. So this is important to set which one of the transition we fire first by system priority, determinism, or random, right? Also, we have the policy-based, the arithmetic for checking and sensibilities, sparse dense matrix, because with the incident matrix, which is the representation of the transition and place of the network, we could have more places than transition or more transition than places, and this is the difference between this kernel. We use the builder design pattern for creating these vectors on the incidence matrix from the information provided for the Golang microservices in the Petri network markup language of JSON, right? And the observer design pattern to, of course, keep the tracking of each one of transition fired and telemetry for notify to this service and the final user. And I say header, the pointer to implementation for GPU, AVX, backend, and stable ABI. We are not using visitor command or another pattern like after factory because we execute the matrix directly. And this is important, I say early, is the essential of using PetriNet. It's the basic only in some operation. We don't need to represent a transition out token or place using objects because we have the possibility to represent this system and the modeling of this system in a mathematical way. So, some approach we are using is the concept approach, because we want to apply this plugin safety about which algorithm we are running. Yes, this contract between we want to execute or not is validated at compile time, so we prevent API drift and runtime errors to the possibility using contracts. We also use MD-span to make a view of the memory of information stored and avoid the copy of large matrix of the instance, and which is stored in this flat buffer. So this is an efficient data flow and preserving the cache locally for firing at dice. We will later see this operation here in this possibility to enable the single instruction multiple data, which is the special registry of the microprocessor for this operation vectorized. And each one of the transitions associated with the network, we created JTreat, automatic generated treat, which allows to use the monitor design pattern, which encapsulates the state and synchronization assigned of object at the monitor, ensuring that only one synchron method executes at a time. We protect the critical section through the object monitor. Also, on implementation of monitor, I will explain later in the next diagram, it has several queues to store the threads that cannot fire the specific transition because it's not enabled. So we serialize the access to share the state and use the wait notify semantics for cooperative execution. Why not use the update object pattern? Because the monitor does not run in a separate thread. Each request executes in the client's thread. So we can keep the invariance and prevent data races. And this monitor, we can see in this block diagram, we have two entry doors. We can imagine this like a commodore room, for example. So we have two people who want to eat. One enter for the red door and another enter for the blue door. This separation is related with some trees are fired in mandated transition, which are transitions that don't have an associated determined or stochastic, and the blue trees are trees and fire stochastic or timing transition. So they have the window fit to make a fire and change the state of the network. So the critical section is here, and each one of the threads trying to execute the fire to change the state of the network. And this is not possible. Enter to appropriate queue and wait until they can enter again to the critical section and produce this change of the network and finally leave the critical section, this dining room. So, the execution model we can also apply not only for one instance of the microprocessor we are running, and for example, is the server environment allow us to use GPU programming. Not only that, we can also try to implement parallel programming using clustering, where we can execute the fire sequencing across multiple microprocessors. And this is the another feature which leads us in a highlight when we are making this project, right? So when we have to our networks, we are not only see the evolution of the network, the evolution of the state of the network, we are also want to analyze the properties related with that network, and the properties related with that network are the properties related with our system. So one of the important algorithms to see in the Petri networks is the algorithm of minimal covariability tree. With this algorithm produce a tree which contains all possible states from the initial states of the network. So we can see what conditions we require to reach a specific state. So, for example, we are modeling a runway system, and we have two trains that can collide in a specific moment. We don't want this happen, and with this covariability tree, we can see what conditions will be necessary to produce this collision of the train and avoid them through our initial marking. We have also cutoffs, heuristics, and deep limit, hash pruning, GPU candidate for parallel frontal expansion. The variance, of course, we can see the P variance or place invariant, this token conservation, T invariance or transition invariance with the cyclic variant sequences, integrate null space via Smith or normal form, and calculate synchronous traps, which are special way to keep the token in the network via strongly connected components and feedback sets. One of the important algorithms I say is the minimal covariability tree, which I previously make a research and implementation of the algorithm for my degree thesis based on the extended equation of the paper format. We implement an optimized minimal covariability tree algorithm. We name it MinCoV, which extends the traditional Kaplan Miller and monotony pruning and MinCoV algorithms with the property of vectorized state updates. In that moment was with C++20. We also keep them the capability of parallel firing and hash-based redundancy filtering and control acceleration, because we can, and this is one of the problems of this algorithm, we can have a particular transition that grows exponentially. And this transition can lead in the infinity loop of trying to keep this firing sequences. So we can detect this specific place where this token increase exponentially and put a symbol omega, which represent infinite for us. And when we have too many place and transition, we have too many possibles. And this is produced a consume of the memory. So this bounding memory through this omega propagation, which activates significant reduction in node count and running time versus the other algorithms. In a simplified way, we have another to analyze the initial node, try to fire transition. If the node is 6, we try to accelerate. We prune the node to avoid keep searching in a node that already have an omega, and keep this in the filter set to keep analyzing. So if we have this representation in a pipeline, when we have every stage, the stage of generation, the stage of checking, acceleration, and pruning, and so on, this is repeated over time. So our plan is make a data layout as SOA, continuous incidence column. I take approach of the cache memory because it's important for quickly make the fire operation. Keep the kernels. This means the incidence matrix and runtime dispatch bit rates. Take the approach of single instruction multiple data, which is especially most present in the most of the processors right now, and it's based in NSTD SMD. Zero copy to flat buffer and views, a lot of views, and execution models to determine for pedagogy and parallel throughput. We have a special research about this determinist of execution of the network we are currently working. Also the metrics, the IPC, instruction per cycle, memory bandwidth, and contention of execution. So one risk and trade-off we consider is, as I said earlier, the cooperative blow-up, because we have too many place and transition, and this could lead too many states. And of course, memory and time capabilities will be reduced. The portability when we're using this accelerated calculation. The safety of zero copy associated with the lifetime of the object, and the API, of course, the C-boundary man-pointer implementation for stability. Also the determinism and speed, which should be the default. We already have the determinism of the network, or we always should consider the speed over anything else. Our philosophy is both them, right? And the stability, because the omega could be a numerical limit, but what happens if this state calculates a new state using this numerical limit, which could be a potential undefined behavior. So we're still analyzing this interface, this good balance. We are using this approach correctly. What determinism we are going to use, default or operational? For concurrency, we should use a thread pool in practice, or start using coroutines to handle this file thread. With metrics and trace, we are tracking every one of the threads that file to transition, or are we using a consume time of each one? What happens when we have hardware acceleration? What if this could not only be a simulator, also be an emulator through FPGA? What if we can connect a system, external system, through sensors and actors, through a HPA, and this HPA connected with our cloud environment to modulate and determine how the system will respond in the real world? So thank you so much for your time. I'll leave you my social networks to keep connected. And thank you, Jens, for the opportunity of share this presentation with all of you.
Thank you for your time and your interesting talk, Gabriel.
Thank you.
If there are any questions, Gabriel should be available in the lounge, and I guess he already has been in the chat. So thank you for your time.
See you there. Thank you.